Before we get started, I have a quick favor. I've been self-funding the Finding Genius podcast for 5 years now. I've done over 3,000 episodes. And as you can see on YouTube, we're up over 1 million views on the channel, which is fantastic. The next thing I really want to push on is to get up to 10,000 subscribers. Because once we do, we'll be able to put a donate button and we'll be able to solicit donations to help keep the podcast running and to also get the Finding Genius Foundation moving along. We have a big project studying anxiety, depression, and PTSD and working on a product to help people overcome these problems because I've seen them explode recently after the last 2 years of the whole virus situation. So if you would, please subscribe to the podcast. That would help us tremendously. Give us a thumbs up and check in the description for Buy Me a Coffee. It's about $5. If you could buy me a coffee, I'd really appreciate it. It would help keep the channel going, and I love coffee. Thank you. Organifi is a line of organic superfood blends that offer plant-based nutrition made with high-quality ingredients. Each Organifi blend is science-backed to craft the most effective doses with ingredients that are organic and free of fillers and contain less than 3 grams of sugar per serving, like Organifi green juice with essential superfoods and a clinical dose of ashwagandha. It helps reduce stress and support healthy cortisol levels. Or Organifi red juice, a superfood punch that increases energy without caffeine and only 2 grams of sugar. Each Organifi blend is easy to use simply by mixing it with water or your favorite beverage while on the go, and they don't compromise quality for taste. Organifi takes pride in offering the best tasting superfood products on the market at a price that works out to less than $3 a day. You can experience Organifi's high-quality superfoods without breaking the bank. Go to Organifi.com/genius and use the code GENIUS for 20% off your order. That's Organifi.com/genius. Use code GENIUS to get 20% off any item. Remember, www.Organifi.com/genius.
Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Before we continue, I've been personally funding the Finding Genius podcast for 4.5 years now, which has led to 2,700 plus interviews of clinicians, researchers, scientists, CEOs, and other amazing people who are working to advance science and improve our lives and our world. Even though this podcast gets 100,000 plus downloads a month, we need your help to reach hundreds of thousands more worldwide. Please visit findinggeniuspodcast.com and click on Support Us. We have 3 levels of membership from $10 to $49 a month, including perks such as the ability to see ahead in our interview calendar and ask questions of upcoming guests, transcripts of podcasts you're interested in, the ability to request specific topics or guests, and more. Visit findinggeniuspodcast.com and click Support Us today. Now, back to the show.
Hello, this is Richard Jacobs with the Finding Genius podcast, now part of the Finding Genius Foundation. I have Dr. Dominic Papineau. He's an associate professor in geochemistry and astrobiology, and we're going to talk about what the oldest fossils on Earth tell us about the origin of life. So, Dominic, thanks for coming.
Well, thank you for having me.
Yeah, tell me a bit about your background and then your current research, if you would.
Okay, well, my background originally was in physics and biochemistry. That was for my undergrad, and then I did a PhD in geological sciences and astrobiology for my PhD at the University of Colorado at Boulder, and then I did a postdoc at Carnegie in geochemistry and also astrobiology in Washington, D.C. And my research is about addressing problems related to the early evolution of life, the origin of life, and developing biosignatures that will hopefully help us to search for life on other planets.
Okay. So what is some of your more research about? What have you discovered recently?
Well, so we have been investigating for the past 15 or so years these rocks I collected in 2008 from the Nuvvuagittuq Belt in northern Quebec in Canada. And so these rocks are from an area that is not forested and where there's not a lot of soil. So the last glaciation there that basically receded about 8,000 years ago left beautifully exposed basement rocks, and so you can just walk on them. And there are some volcanic rocks in that Nouveau-Agituq belt that have been dated directly to be 4.28 billion years old. So they're extremely old, and they're potentially thus the oldest rocks on Earth. And they contain sedimentary rocks, which we reported in 2017 to contain the oldest fossils. But there was quite a bit of controversy then, and now this recent paper addresses these controversies.
Well, when you say oldest, what was the oldest? I guess these were stromatolites that were 3.6 billion years old, and the ones that you found are a lot older, or what's the numbers look like?
Right. So the oldest evidence of life that we had before that was pretty well accepted by the community dated back at around 3.5. That's right, 3.5 billion years ago. And they came in the form of stromatolites and some microfossils from both Western Australia and South Africa. But now, these ones, they push the clock back quite a bit more, and they have different kinds of biosignatures because they were probably not deposited in the photic zone of the water column, so not where there was sunlight penetrating. It was too deep probably for sunlight to penetrate where these sediments originally accumulated.
The ones that you found, are they multicellular life, or are they single cell life, and where do you think they came from? Back then, how old are the ones that you found, and then what was their structure? Let's start with that.
Right, okay. Well, the microfossils that we found, they are probably just as old as the rock. It's very difficult to conceive that they would be younger than the rock given their geological context. But also, when we look at them in the microscopes, they are quite recrystallized. So they've been affected by high temperature during a very long residence time in the crust, and that has affected the minerals. It made some minerals grow larger sizes, which is what happens when you melt a rock, or in this case, the rock was not melted, but it was certainly exposed to high temperature for quite some time. So we see this thickening of some of the filaments that we discovered. The filaments are made of hematite. It's a kind of rust, iron oxide. And they form these organized structures that look a little bit like a comb. So they're all branching on one side and parallel aligned, as well as they have corkscrew shapes. Some of them are also in tubes, and within these comb-like structures, we also see small granules with many microfossils of another kind, which are these irregular ellipsoids. So they're kind of these little balls that are not quite spherical and not quite perfect. So call them irregular ellipsoids, and they're also made of hematite. So it's not clear that these were multicellular. I don't think they were, but they were probably a microbial community metabolizing the environmental compounds that were available in this kind of environment, which was hydrothermal.
Yeah, but were they ordered by microbes just being at the right places in a vein of rock? So they took on the rock structure, or do you think that this was actually an organism or a biofilm that had its own structure and became frozen into a certain structure and that was preserved? That's what you see.
Right. This is what basically we're seeing is, and I think the best analogs that we can think of are those that live today on the modern seafloor in places where there is hydrothermal activity, like, for instance, the Loihi volcano of Hawaii, which is still a submarine volcano. There's no island there, but it's a mountain. It's an underwater sea mount, which has these kinds of pods of silica. It's kind of a gel, like toothpaste probably. It's a silica gel that's enriched in iron oxides, and there are myriads of microorganisms that live in these places. Near Hawaii, I said, but also in other volcanoes in northern Atlantic to Arctic Ocean and in the Indian Ocean as well. So we see these kind of limited, isolated pods in the vicinity of hydrothermal vents in the deep sea, and they are basically metabolizing the iron and sulfur that's coming out of the vents. So this is what we see today, and our data independently confirm that this has been taking place for a very long time, since potentially since the origin of life.
Well, you said that these fossils are yet a lot older than ever discovered. So how old do you approximate?
Well, so the fossils are, I believe that they're just as old as the rocks, so that would make them 4.28 billion years of age. But there is some controversy about the age of the rock. There are groups of experts who believe that these rocks are actually much younger at 3.75 billion years of age, which would still make them really, really old and still the oldest microfossils that we know of. But these groups explain the age of the volcanic rocks in the belt as some kind of inherited age from a very early kind of primordial mantle reservoir. So that means that the age of the volcanic rocks is not reliable. I think that it is reliable because there's also independent observations of other rocks that are about 4.0 billion years that intrude the belt. So these are gabbros, and it's quite typical of ophiolite sequences that we see in younger localities around the globe.
So have you ever seen the kind of structure that you see in these rocks in nature? Or
Yes.
has it only come from, has it ever come from an abiotic source, or has it only come from a living source, the structures you see?
Right. This is another point of contention, of course, can they be explained by abiotic processes? We mentioned already the first point of contention are those things as old as the rock. Now that's the second bit. The possible abiotic origin of some of these features is probably likely. Now we found a number of different kinds of spherical objects in there that look like they're fossils, but they're probably not. They're probably pseudo fossils. So they just look like fossils, but they're probably abiotic structures. But the problem with invoking this for all of our observations is that to make this fit with the chemistry that's necessary, you would need to have compounds that are not compatible together. So that there are abiotic structures, microscopic structures, that look like corkscrew-shaped filaments, that look like irregular ellipsoids that I mentioned earlier, and that look like some of the tubes that we've also reported. But none of these abiotic reactions currently known can form those comb-like structures or the pectinate branching filaments of hematite. These are quite exceptional. So I mentioned we found similar analogs in modern environments, but indeed they occur throughout Earth history. There are examples of similar kind of pectinate branching filaments in the Figueroa jasper of California, which is Jurassic in age, and there are also others in kind of Earth's Middle Ages that are around 2 billion years old from Arizona and from Minnesota, also in the United States. Some others have been also reported from Svalbard, from Norway, from the Ural Mountains. So there's quite a number of examples with which we can compare our structures.
Oh, good. Okay. So the most compelling feature is the comb-like structure that seems the least likely to be abiotic in nature.
That's correct.
Okay. And then you're thinking the age is 4.28 billion. Crazy. If you were able to go back in time, what would this look like when it was, I think it was a biofilm or a multicellular creature?
Yeah, that's a great question. I like to put my mind into the mindset of an astronaut on Mars who would basically be looking at jaspers and chert like this, these kinds of rocks, and that would specifically look for nodules in them, which is the object in those rocks in which we find the microfossils. So this is kind of what we have to look for, and these are the kinds of features that might indicate a very early biosphere on another planet. And so, this is very exciting. It's quite revolutionary because pushing the clock back so much implies that the time for the origin of life is very short. And if the time for the origin of life is short, then the probability that it exists and that it is widespread is greater.
Well, is it close enough where it was coincident with the Earth settling from its most molten state? At the moment that it had become just non-molten enough to accommodate anything, life was there. Does it tell you that life started pretty much immediately at the moment it could start?
Well, it started very early. Yeah, there is indeed a hypothesis, or a model that the early Earth was covered by a so-called magma ocean, which is basically kind of a hardened, very thin crust with a lot of rifting and tectonic activity, I guess. But this is not clear how much tectonics there was and how much volcanic activity there was. There is no record that is older than this that we have from Earth. All the other older rocks than these ones are either from the moon or from Mars or from meteorites. So back then it was a time that was anoxic, so there was no oxygen in the air. So the sky would not be blue; it would probably be kind of a grayish, maybe greenish color. But still, there was a hydrological cycle very early in Earth history, and we know that from other evidence, from some zircons in Western Australia, that have the signature, some specific isotopic signature that tells us that there was an ocean at least 4.4 billion years ago. So very quickly, very early, you have these quite complex life forms emerging. And perhaps the most surprising thing that I did not mention is the sheer size of these filaments. So the comb-like structure is about 1 centimeter in size. So we could see this to the naked eye if the rock was broken. I mean, I can see this naked eye in a specimen in the freshly broken face or in a polished face of the rock. So, yeah, an astronaut on Mars would be able to specifically look for this, which makes this extremely exciting because you don't necessarily need a microscope to search for these things, but it will be necessary to confirm.
Organifi is a line of organic superfood blends that offer plant-based nutrition made with high-quality ingredients. Each Organifi blend is science-backed to craft the most effective doses with ingredients that are organic and free of fillers and contain less than 3 grams of sugar per serving, like Organifi green juice with essential superfoods and a clinical dose of ashwagandha. It helps reduce stress and support healthy cortisol levels. Or Organifi red juice, a superfood punch that increases energy without caffeine and only 2 grams of sugar. Each Organifi blend is easy to use simply by mixing it with water or your favorite beverage while on the go, and they don't compromise quality for taste. Organifi takes pride in offering the best-tasting superfood products on the market at a price that works out to less than $3 a day. You can experience Organifi's high-quality superfoods without breaking the bank. Go to Organifi.com/genius and use the code GENIUS for 20% off your order. That's Organifi.com/genius. Use code GENIUS to get 20% off any item. Remember, www.Organifi.com/genius.
But based on the dimensions you're talking about, this means billions of cells working together in an organism, or does it mean, again, I can't see how a biofilm would make the structure, but what do you think? Again, if you were there, sitting there with this thing, what would it look like when alive?
Well, I think these were, so we call them benthic microorganisms, meaning that they're attached to the seafloor. That's as opposed to pelagic, which kind of float in the water column somewhere and drift away with currents. Those ones were attached, and they may have work in a form of symbiosis together in order to filter out metals from seawater or potentially share the little fixed nitrogen that was there or sulfur. But they were commonly probably metabolizing iron. This is what we can infer from their morphology and the comparisons that we can do with the modern examples, the modern analogs.
Oh, is that why the structures were filled with hematite?
Well, yes, exactly. So the modern organisms, the modern iron oxidizing bacteria, they take a substance called ferrous iron, and they take an electron from it. So it's basically their sugar. For us, it's sugar. We take electrons from sugar and cake and chips. And then these organisms, they were basically taking electrons from this form of iron called ferrous iron, and they were making it a ferric form of iron, so essentially rust, where it becomes, not soluble in water and precipitates, and it encrusts the cells. And the cells who do that today, they're kind of, they're really exceptional microbes because they've been around for an extremely long amount of time. But they basically encrust themselves, and very often that results in cell death. If they take too much iron, they encrust themselves, they die, and then another generation continues to do the same thing. So they grow in layers. So we know these environments exist today, and we know they're populated by microorganisms, and they're not multicellular, although they seem to have been working as a community, a diverse microorganism.
Well, is this a persistent biofilm type structure that builds up over time? Is this like a coral, essentially? Like, what would be the closest analog that's around today to what this thing is?
Right. So as I mentioned earlier, so you have these kind of pods, isolated pods of silica, and it's a silica gel and ferric iron. So they're kind of reddish orange patches of fluff, really, on the seafloor today, near hydrothermal vents. So they're directly sitting on top of pillow lavas, like you see sometimes forming underwater. We have pillow lavas, by the way, in the belt, in the Nouveau-Guadeloupe belt. But the pods themselves they contain a lot of iron, so that comes from somewhere. That must come from exhalations from hydrothermal vents. And that's what makes this exciting, is because microbiologists have been telling us for 40-something years, since the discovery of hydrothermal vents, that life most likely originated there. So now we have direct evidence for that.
I don't know. Any thoughts that was there life even simpler than this? Was there life that predated this, what you found? Is there any way of telling, is there even more to find out there that's even older?
Well, possibly, but then we run into the problem of preservation and whether or not there are rocks that are sufficiently well preserved that are older, and we don't know of any right now. But, as the global warming continues, one of the maybe only positive things is that it exhibits more outcrops of bedrock in Greenland and Antarctica, and we don't know what's lying underneath there. And actually, in 2016, there was a paper that reported stromatolites, as you mentioned earlier, from Greenland, and these are thought to be 3.71 billion years of age. So they were discovered because ice has receded from these outcrops in the past 20 years. So that has exposed them and allowed geologists to document them and sample them. So maybe that's to be found in the future, but rocks that are older than that are extremely rare, or older than 3.7 billion years. There's just maybe 4 or 5 places on Earth that are currently known to have them.
Well, I guess just like the beginning of the universe, we can only go back so far, and then there's this curtain where we can't go back any further because of the nature of physics. With the formation of Earth, how far back do you think we can go? Like you said, we're down to only 4 or 5 places that might have rocks or structures this old, but what do you think is going to be the fundamental limit? Like, how close are we?
Well, I think we're very close to the limit. Some people have suggested that maybe there's some very much younger rocks on the moon, so from Earth, so the rocks that have been maybe ejected during these cataclysmic impacts on the early Earth that would have maybe floated around in Earth's orbit for some time until they fell on the moon. So maybe the moon has some of these fragments, but that's literally a needle in a haystack. In terms of outcrops and basement rocks, we're out of luck. We're out of luck, but that's because we have a great planet. It's got active plate tectonics, which recycles carbon in the mantle, and that's very important for the carbon cycle. So if we didn't have this tectonic recycling of old rocks, we wouldn't have the carbon cycle that we have today, and probably maybe a planet like Mars, potentially a dead planet, or also potentially habitable. But you know what I mean, I think.
I would guess people model the Earth back in time, and they go back to Pangaea, and I'm not sure what would be around about 4 billion years ago. But what does this suggest? Like, what places on Earth do you think, if we're going to find even older stuff or more complementary stuff, same age, where is it going to be most likely?
Well, I don't think it would be exposed today. So I don't think if you look at a world map, every continent that is exposed, I don't think there will be any older rocks where the rocks are exposed on continents. But as I said, potentially in southwest Greenland, as well as in Antarctica, in East Antarctica, there are some very old pieces of crust there. And as the glacial ice caps are melting away, I mean, they will eventually expose more rocks underneath. So this would probably be the best place to look for, but it's a future thing.
Is it the hematite you found Would that occur today, or what happened? Do you think that I guess this amalgamation of archaea or bacteria, whatever it is, it got covered over and then died, and then what the hematite started forming inside of its own internal structures over time, or
Right.
how do you think this also came to be?
So what we see today is that the iron oxidizing bacteria, they precipitate a mineral called ferrihydrite. So ferri means it's ferric iron, so with one electron less, and the hydrite relates to water. So the ferrihydrite, when it's exposed to geological condition, will lose that water, and then it is converted to hematite, which is why we see them preserved as hematite. But it is the same thing as what we see in similar environments that are younger, like, for instance, Milos in Greece, a few million years old. I mentioned the Figueroa jasper of California. These are all preserved in hematite now.
How long does the process happen? Like, what's the approximate speed that you've observed it?
Well, we haven't done these kinds of experiments. That would need to be answered with experiments in the lab. And I don't know that people have really figured this out. It's probably on the orders of months to years based on how quickly concretions form in nature. We know of some concretions that have formed since the Second World War. So these objects can form over years. It's not so long.
What was the dating method you used, and why is there controversy there?
Right. So we didn't do any dating. This was done by another team that was based at McGill. So the work was done on the volcanic rocks, as I mentioned, and the isotopes that were looked at were it was samarium-146, which decays with an alpha particle to neodymium-142. That decay is very quick. It's about 100 million years. So very quickly, after the formation of the solar system, where there was some samarium-146 in the solar nebula from the supernova explosion that is necessary to create large atoms like this with so many neutrons and protons, the samarium existed for just a few 100 million years on the early Earth. And then all of it was turned into neodymium-142. So these rocks, the volcanic rocks, have very unusual signal in neodymium-142. Actually, it's a unique signal worldwide for rocks of that age, and it has been interpreted differently by different groups. I believe it is certainly consistent with a Hadean age, so a 4.28 billion-year-old age, because that's what also this data tells us. But others argue that it could be from an older source of the mantle that was inherited in the rock, that was of that age, and that the rock ultimately is just 3.75. So there's controversy on the age also because of the different interpretation of these intruding gabbros, which is a kind of a mantle rock, a very black rock in the belt, which are 4.0 billion years, dated with the same technique, but they are therefore giving a minimum age to the belt at 4.0. But the groups who think that these are all inherited ages. So it's unresolved now. I think that the way forward will continue to be to generate more data on different isotopic systems to have independent confirmations of one or the other conclusions.
Where in the world was this found?
So this was found in northern Quebec in a region called Nunavik. So it's part of Canada, and it's on the shore of the Hudson Bay. Very cold place. Mosquito infested in the summer, but absolutely wilderness beauty. Fantastic place to visit. No trees, beautiful animals, wildlife. You can drink from rivers, from creeks. It's a wonderful place.
Any idea, 4.28 billion years ago, where this would have been on the planet? Same spot? What would have been around it, etc.?
Well, this would probably not have been at the longitude and latitude that we see them today. This is kind of located in the close to the middle of a very old piece of crust that's in Quebec and Ontario, the two provinces of Canada, which forms the superior shield or the superior craton. So it's a very old root of the continent that's sitting there, and it's probably been drifting for huge amounts of distances over billions of years, and it's been subducted, so buried quite deep, depth of probably several kilometers, if not more than 10 kilometers depth. And then, eventually some mountain building events happened, and these rocks came closer to the surface, and now they're currently weathering. They're exposed to the atmosphere. So there's patches of soil, patches of grass and lichen. But they're there. We can see them. We can walk on them. They're beautiful rocks.
Yeah, very cool. So what's next in your research?
Well, we want to look more into the composition of these filaments. So we've already seen that there's these two forms of iron within them, so ferric and ferrous iron, which we see also in modern filaments. So we want to see more. We want to see some carbon in there. What kind of carbon, what kind of trace elements and trace metals, and even their isotopes, which could enlighten us as to what they were eating, what they were breathing, these microorganisms. And that can in turn tell us something about the early evolution of these biological metabolisms and these lines of descent that still exist today, that still do the same thing in the same kind of environments.
Yeah, very cool. So Dominic, where can people find out more about your work and maybe see pictures of the rocks that you're talking about, the fossils?
Right. So there's a video that's been uploaded on YouTube. It can also be found on the Earth Science Department webpage at University College London, where I'm based. And there's a lot of news articles also out there. So you can just Google oldest microfossils in Jasper, and you'll probably see some reports and various pictures there that I've been providing to the media. But I'll be happy to provide you with anything you may need also for this.
Yeah, no, that's great. If you get a few pictures for the show notes. So, yeah, Dominic, thank you. Keep up the good work, and keep looking for even older stuff as friends at the same time. And thanks for coming on the podcast.
Yeah, thank you very much for having me and for your interest in this. Thank you to your audience as well.
Organifi is a line of organic superfood blends that offer plant-based nutrition made with high-quality ingredients. Each Organifi blend is science-backed to craft the most effective doses with ingredients that are organic and free of fillers and contain less than 3 grams of sugar per serving, like Organifi green juice with essential superfoods and a clinical dose of ashwagandha. It helps reduce stress and support healthy cortisol levels. Or Organifi red juice, a superfood punch that increases energy without caffeine and only 2 grams of sugar. Each Organifi blend is easy to use simply by mixing it with water or your favorite beverage while on the go, and they don't compromise quality for taste. Organifi takes pride in offering the best tasting superfood products on the market at a price that works out to less than $3 a day. You can experience Organifi's high quality superfoods without breaking the bank. Go to Organifi.com/genius and use the code GENIUS for 20% off your order. That's Organifi.com/genius. Use code GENIUS to get 20% off any item. Remember, www.Organifi.com/genius.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at FindingGeniusPodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.